Hi everyone, this is Supriya from KPR Institute of Engineering and Technology. So in this video we are going to see half adder and full adder. In this video we learn about the half adder and full adder circuits. First let's start with half adder. So this half adder is the combinational circuit which adds the 2-bit and gives its sum and the carry bit as the output. Let's see what is the logic circuit of this half adder. For that, we have to use truth table. First of all, let's understand that when we add the 2 bits, then what are all the possible outcomes? For the 2 bits, there are total 4 different combinations, right? So here 0 plus 0 is equal to 0. That means whenever A and B is equal to 0, its sum bit and carry bit both will be 0. Similarly, this 0 plus 1 is equal to 1. This means sum is equal to 1 and carry is equal to 0. Likewise, 1 plus 0 is equal to 1. That means whenever A is 1 and B is 0, then this sum bit is equal to 1 and carry bit is equal to 0. Likewise, 1 plus 1 is equal to 0 with 1 as a carry. That means whenever that is both A and B is equal to 1, then the sum is equal to 0 and carry bit is equal to 1. This is the truth table of the half adder. So, as you can see, this sum output is equal to 1 when A is 0 and B is 1, or when A is equal to 1 and B is equal to 0. If we see the Boolean expression of this, that is the sum output, it is equal to A XOR B plus B bar, or it is equal to A XOR B. Similarly, this carry bit is equal to 1 when both A and B is equal to 1. Therefore, if we see the Boolean expression of this carry bit, that is equal to A dot B. These are the Boolean expression of sum and carry. Now let's implement them using the logic gate. As you can see these expression, the sum output can be implemented using two input XOR gate, while the carry output can be implemented using two input AND gate. This is the logic circuit of half adder. Now this half adder circuit works perfectly when there is no incoming carry. But if there is an incoming carry from the previous addition, then we cannot add that carry using this half adder. For example, let's say when we add these two binary numbers, now the LSB of these two binary numbers can be added using half adder because during the addition there is no carry. So after the addition, this is sum bit is equal to 0 and the carry is equal to 1. Now in the next column if you see, we have the carry bit along with these 2 bits, and this carry bit is generated from the previous addition. So if we try to do the addition using this half adder, then simply we need to ignore this carry bit, and that is the limitation of this half adder. That means using half adder we cannot add the carry which is generated from the previous addition. So if we want to add 2 bit along with the carry bit, it can be performed using full adder. So this is the full adder and it is the combinational circuit which adds 2-bit and the incoming carry bit, which generates sum and carry bit as the output. Let's see the logic circuit of this full adder. For that, let's see the truth table of this full adder. Here, for 3 inputs, we have total 8 different combinations, right? So here in the first row, that is 0 plus 0 plus 0 is equal to 0. That means sum is equal to 0 and the carry bit is equal to 0. Similarly, 0 plus 0 is equal to 0 and then this 0 plus 1 is equal to 1. That means in the second row, the sum is equal to 1 while the carry bit is equal to 0. In the third row, 0 plus 1 is equal to 1 and then 1 plus 0 is equal to 1. That means in the third row, the sum is equal to 1 and the carry bit is equal to 0. Likewise, in the fourth row, 0 plus 1 is equal to 1 and this 1 is added with another bit 1 which gives 0 with carry as 1. That means in the fourth row, the sum bit is equal to 0 while the carry bit is equal to 1. Likewise, in the fifth row, the sum bit is equal to 1 while the carry bit is equal to 0. Similarly, in the sixth row, 1 plus 0 is equal to 1 and 1 plus 1 is equal to 0 with carry as 1. That means sum bit is equal to 1, the carry bit is also equal to 1. Similarly, in the seventh row, 1 plus 1 is equal to 0 with 1 as carry, and then this 0 plus 0 will be equal to 0. That means the sum bit is equal to 0 when the carry bit is equal to 1. Finally, at the last row, 1 plus 1 is equal to 0 with 1 as carry, and then 0 plus 1 is equal to 1. That means 8th row, the sum bit is equal to 1 and the carry bit is also equal to 1. So in this way we got the truth table for the full adder. Now we can see this sum bit is equal to 1 for 4 different input combinations. Likewise, the carry bit is equal to 1 for 4 different input combinations. Now let's find out the Boolean expression of this sum bit and the carry bit. And then let's try to minimize this Boolean expression. As already said, this sum output is 1 for 4 different input combination. This Boolean expression of the sum output. So now in the first two terms, we will take A bar as common. Then in the bracket, we will have this. That is B bar C in plus B C in bar. And then it is equal to B XOR C in. Similarly, in the last two terms, if we take A as common, then in the bracket we will be having B bar C in bar plus B C in, and it will be equal to B XOR C in, or it is equal to B XOR C in the whole bar. That means we can write the expression as A bar in the bracket B XOR C in plus A dot B XOR C in the whole bar. Now let's say this B XOR C in is equal to X. That means we can write the expression as A bar X plus A X bar. And it will be equal to A XOR X, or we can say it will be equal to A XOR B XOR C in. That is simplified expression of sum output. Let's see the minimal expression for the carry output. Now we can see from the truth table, the carry output is equal to 1 for 4 different input combination. This expression of carry output. So now we can find out the minimal expression using the K-map. Here is this A bar B C in corresponds to the min term, that is M3. Similarly, this A B bar C in corresponds to min term M5. Likewise, this A B C in bar corresponds to the min term M6, and this A B C in corresponds to the min term M7. Here we can make the group of this M5 and M7. Similarly, M5 and M7, and also we can group M6 and M7. Likewise, we also group M3 and M7. Here in this group, it corresponds to BC in. Similarly, this group in the yellow color corresponds to AB, while the blue color corresponds to AC in. So, if we see overall minimized expression for this carry output, it will be equal to AB plus BC in plus AC in. Apart from that, we can also write this C out in the different way. So if we see the last two terms, the expression that is AB will be common. So let's take it outside. Similarly, in the first two terms, C in will be common. So if we take C in outside, then we will be having A bar B plus A B bar, which also corresponds to A XOR B. Similarly, the first term, that is C in plus C in bar, which will be equal to 1. That means we can also write the expression as AB plus C in into A XOR B. This is the another way of writing the carry output. Let's see the second way of writing the output of Cout. Apart from this, the carry output can also be written as AB plus BC in plus AC in, and the sum output can be written as A XOR B XOR C in. Now we can see the logical circuit of this full adder. First, this sum output will be equal to A XOR B XOR C in. So it can be implemented using two XOR gates. The output of first XOR gate is equal to A XOR B, and it can be given as an input to the second XOR gate. And the second input of the second XOR gate will be equal to C in. So the output of second XOR will be equal to A XOR B XOR C in. Similarly, the Boolean express from the Boolean expression, Cout can be implemented using three AND gates and one OR gate. So this is the logic circuit of full adder. So Cout will be equal to AB plus C in into A XOR B. So using this part, we can generate the carry output. So this is the another way of generating the Cout. Here the output of first XOR gate is applied to the AND gate, and the second input of the AND gate is equal to C in. That means the output of this AND gate is equal to A XOR B into C in. And using this OR gate, the output of two AND gate is logically OR, and this is our output Cout. So this is the another way of generating the Cout. So if we observe this, we can see XOR gate and the AND gate, which is nothing but the half adder. Similarly, the XOR gate and the AND gate forms the second half adder. So using the two half adders and one OR gate, we can generate the full adder. So the half adder consists of one XOR gate and one AND gate. Instead of representing it with logical circuit, we can also represent it with half adder block. So inside the half adder, it consists of one OR gate and one AND gate. So if A and B are the input of this half adder, the carry output will be equal to AB, while the sum output will be equal to A XOR B. Now the sum output is applied as an input to the second half adder, and the second input of this half adder is equal to C in. So the sum output of this second half adder will be equal to A XOR B XOR C in, and similarly A dot B. The carry output will be equal to C in. Now after the first half adder, the full adder circuit which we have discussed already, which we have to add two 1-bit numbers along with the carry bit. But if we want to add two n-bit numbers, then we need to use n number of such full adder blocks. Thank you everyone.